Okay, this is the Chapter 6 lecture guide, and you can see the table of contents there. If you want to look things up, this is 6 and 7 in one lecture guide. If you want to look at electromagnetic radiation, you ask why we want to look at that when this chapter is about atoms and atomic structure, because a lot of what we know about atomic structure is because of how the light interacts with particularly the electron levels in our case. Electromagnetic radiation behaves as a wave, which means it has a wavelength with a symbol lambda. This is the distance from the top of one wave or crest to the top of the next wave, or an equal point on one wave to an equal point on the next wave. Wavelength is measured in units of length, like meters, nanometers, centimeters, so on and so forth. We'll focus a lot on nanometers in this chapter because visible light usually is measured in nanometers, and a nanometer is 1 times 10 to the negative 9th meters. If it has a wavelength, it has a frequency, and the frequency has the symbol of the Greek letter nu. It looks like a little script or cursive V. It's the number of crests or troughs that pass by a given point in 1 second. So it'll be measured in units of 1 over time. And if that is seconds, you'd have 1 over seconds, and a 1 over seconds is hertz, and hertz is a cycle per second. The relationship between wavelength and frequency is that the velocity of the wave is equal to the wavelength times the frequency. For electromagnetic radiation, the speed of light is 3 times 10 to the 8th meters per second. That's really fast. You should know that constant for the test. And if you have the speed of light, that V for velocity becomes a C for speed of light. And so the relationship then becomes C, the speed of light, equals the wavelength of the light times its frequency. If we look at 2 different wavelengths of light, we see one that looks more like a long spread out wave, where the waves are much closer together. And so if you look at that equation, the product of the wavelength and the frequency is equal to the velocity, or the velocity of light in this case. So a shorter wavelength is going to equal a higher frequency. So that second graph with the shorter wavelength would have the higher frequency. We like to look at the electromagnetic spectrum because different regions of it do different things. A lot of times we just refer to the light as light because really all electromagnetic radiation is light, more generically speaking. So if we go from low energy to high energy, we have pretty long wavelength, low energy end of radio waves, then microwaves, then infrared, then visible, and then ultraviolet, then X-rays, then gamma rays. The behavior of that light depends on the region that it's in and consequently its wavelength. The electromagnetic radiation interacts with single atoms or molecules, and it can cause certain behaviors to occur. This is just a little table with the regions and what they're good for, and so we'll quickly go through those. Radio waves are just what you think they are: your AM, FM radio stations, your TV signals, your cell phones, CB radios, any of a number of things like that. Microwaves are sometimes used in communication, astronomy, and in microwave ovens. You said that's pretty low. Usually low energy light is not harmful, but microwaves excite water molecules and make them rotate, and that generates heat, which is how it cooks. And since we're made of mostly water, microwaves can harm us if we get a large enough dosage, because it will generate a lot of heat and start cooking your tissue just like something you put in the microwave. Infrared, a lot of night vision and thermography, or tracking heat, is involved with infrared. People will take infrared pictures of your house and show you where you're losing heat and try to sell you home improvements, for example. Visible light is just what you think it is. It's the light we can see. Ultraviolet, that's where we can start getting the higher energy things that cause tissue damage. We're talking about sunburns and things like that. Fluorescent lighting has a little bit of UV in it. So it's not as the most efficient way, but you can purify water with UV. Water is a good naturally occurring sterilization agent in large enough dosage. Solar panels can work in the UV range as well. X-rays, just what you think they are, medical imaging. You get a medical or a dental X-ray, you can see the bones and goes through the soft tissue. Gamma rays, medical radiation therapy if you have cancer, oftentimes it's gamma. And NASA's been using it for years and years to sterilize foods and increase shelf life on those long space trips. Now, for the visible spectrum, we can split that into colors because we can actually see the different regions of that range of the spectrum. So you got red, orange, yellow, green, blue, and purple. Some people will say, instead of purple, indigo and violet. Some people argue whether indigo is its own color or not, but I'll just let you decide on that. But the red end of the spectrum is the lower energy, long wavelength end, and the purple end is the shorter wavelength, higher frequency end. So that brings us to our first problem. Let's use that frequency wavelength equation. We want to determine the frequency of green light if the wavelength is 520 nanometers. All right, let's look at this problem. I've given you the wavelength. There's the formula. We're going to convert this to meters, or it won't go into this formula because speed of light is in meters per second, so this needs to be in meters before it's going to work out. So we're going to do a quick unit conversion. We're going to convert nanometers to meters, 10 to the negative 9th meters to 1 nanometer. Nanometers cancel, we get 5.200 times 10 to the negative 7th meters. Now we're ready to work our problem. We want the frequency, since we know the wavelength and the speed of light, so the frequency is equal to the speed of light divided by the wavelength. Plugging in, we get 3 times 10 to the 8th meters per second divided by 5.200 times 10 to the negative 7th meters, which, see, that's why we did that, so those units would cancel properly. So then we get 5.77 times 10 to the 14th. Now the units would be 1 divided by seconds. Sometimes that will be given as seconds to the minus 1 power. Anytime you see something to the minus 1 power, that means it's in the denominator, and that would be the equivalent of saying 5.77 times 10 to the 14th hertz. And so that would be your answer. But sometimes it is better to leave it in seconds like that so that you can see the units cancel a little bit more explicitly until you're more familiar with it. Now, in 1900, Max Planck studied black body radiation and realized that there wasn't really an adequate explanation. Something called the ultraviolet catastrophe happened. That is, if you heated something, the wavelength gets shorter, which means you get the higher and higher ranges of light, and that you didn't get as much UV at a certain temperatures as you thought you would. And so he tried to explain that, and he found that the energy is quantized. That is, there's only certain allowed values for the energy, and that light has a particle-like character. I'll link a video to this presentation with what they call a blackbody radiator so that you can see how that works. But the net result is Planck's equation, where he assumed that based on the wavelength of the frequency, each particle of light or photon has a certain energy. So these equations are per photon, where a photon is a particle of light. And so the H in that equation is what we call Planck's constant, and it is 6.626 times 10 to the negative 34th joules times seconds. Which brings us to the next question. If we got that same green light, 520 nanometers, we want to know what the energy of 1 mole of those photons are. Okay, this problem plays off of the last one, so I left it visible. We just calculate that frequency. You can calculate it either from the frequency or the wavelength. It doesn't matter which. Since we just calculated frequency, I'll go ahead and use it. E equals h nu. So Planck's constant, if you remember, 6.626 times 10 to the negative 34 joules times seconds. Now it'll be a little bit more useful to plug in the frequency with seconds here so that you can see that it in fact cancels. Seconds to the minus 1. We can see those cancel, and we're left with running that through our calculator and saying 3.82 times 10 to the negative 19th joules. But this equation is per photon. So if you just ask for the energy of one photon or particle of light, that would be your answer. But that's not what this problem asked. It said per mole. So we want a mole of photons. So to get the energy per 1 mole of photons, we're going to take our previous answer, 3.82 times 10 to the negative 19th joules per 1 photon, and multiply that by Avogadro's number, 6.022 times 10 to the 23rd. And that's going to be photons per mole. Photons cancel, and you're going to be left with 2.30 times 10 to the 5th joules per mole. Or if you want to knock a couple of decimal places off that, it could be 230, 3 significant figures, kilojoules per mole. Either of those would be acceptable since I didn't specify a unit in that case. Next, we'll talk about the photoelectric effect. Now, most people thought Einstein won his Nobel Prize for the theory of relativity, but he actually won it for the photoelectric effect, which was much more widely accepted at the time. It turns out the theory of relativity wasn't widely accepted for some amount of time. So he didn't quite get the credit he deserved for that until later. But in the photoelectric effect, you find that if you have sort of a vacuum tube where you can strike a particular metal, in our case, or it could be some other substances, with light of a certain threshold energy, particularly in the visible and ultraviolet range, then it will eject an electron and you'll cause an electric current to flow. And then you can measure that on an ammeter, or you can use it to perform some sort of electric work. It does have certain applications, like electric door openers that would say open when it was daytime, because once it got enough light to get a current, it would know to actually open the door. The light switches for street lights, if they came on at a certain time, or when the light got below a certain amount, that current gets below a certain amount, it says, oh, it's too dark, and the lights kick on. Exposure meters for cameras, if you have an auto flash feature, that there's going to be a little nodule on the front of your camera that measures how much light there is, that uses the photoelectric effect, and it'll tell you whether the flash needs to come on or not. And again, Albert Einstein won his Nobel Prize for that. In 1921, he won the Nobel Prize in Physics.